Coming up next on Arizona Horizon, a Science Matters special. Renowned physicist and best-selling science writer Lawrence Krauss will join us to discuss cosmic rays and nanolasers and the science behind global warming. That's next on this special edition of Arizona Horizon.
Arizona Horizon is made possible by contributions from the Friends of Arizona PBS, members of your PBS station. Thank you.
Good evening and welcome to this special edition of Arizona Horizon. I'm Ted Simons. Each month, Arizona State University physicist Lawrence Krauss joins us to offer insight into the big science stories of the day, which on this day include new information on cosmic rays, a new gravity measuring device, and the latest science involving global warming. We welcome Lawrence Krauss to Arizona Horizon. Good to see you.
Happy holidays.
Thank you. Well, thank you so much.
This is a holiday edition, and I want to be festive by beginning with bad news.
Okay, well, let's start with, I'm assuming you mean global warming. We have extreme weather, this new report showing increasingly the human footprint is at play. Talk, please.
Yeah, just before actually just before and actually during probably the big news on November 8th. You remember what happened on November 8th?
I do.
It was not what you think it was. It was that the World Meteorological Organization produced a report for the last 4 years saying that they were the hottest years on record. And in every way, they broke previous records. And the decrease in Arctic sea ice, 28%. In every way, it's indicating that we are actually, while we're trying to do a treaty that will cause the world to stop from warming by more than 2 degrees centigrade, we've already up to what at that point 1 degree. We've already gone almost all the way there, and then what's happened actually since the election, about November 14th, they produced their new report. Up to that point, they'd said 2011 to 2015 were the warmest years on record. 2016 beats 2015. 16 of the last 17 warmest years on record have been in the 20th century. 2016 is now on par to be 1.2 degrees above the previous average. So we're already creeping up. And we're already seeing evidence of sea level rise, and in fact, in various parts of the globe, extreme temperature changes compared, in the Arctic especially, much warmer temperatures than were expected before. And sea ice way down, which means sea levels are rising, and it's even worse because when the ice melts, you know what color is ice?
The last time I checked, it was white.
Yeah, it was white, and it reflects the light. Water isn't. It absorbs sunlight. And so the ice, as it goes away, means the albedo, as it's called, of the Earth changes, and we absorb more solar radiation, which means we heat up even more. So it's sort of a nonlinear effect. It's bad news all around as far as the climate is concerned.
We have a map here that seems to show, obviously, the red is going to be warmer, and the differential here between the average, and the blue is not. First of all, obviously, as you said, the Arctic, it's a mess. It doesn't look. Why is what's going on there?
The problem, the thing is that, and it's really important to realize that global warming is not uniform throughout the globe because things like ocean currents are affected. And in fact, the ocean currents that are dramatically affected. So, for example, they affect the salinity of the water and the ability to carry heat from one place to another. And so what you find is that, in fact, it is true that there are colder areas off the Arctic down below near Antarctica, although right at Antarctica it's actually much warmer. If you look right at the coast of Antarctica, right near the bottom,
yeah, you can
and
see
that's where you're really concerned, because you don't care if ice melts when it's already floating. It's the ice that's on the land, because when ice melts when it's already floating, it doesn't change the sea level. It's an interesting bad physics. Put some ice cubes in water,
yes,
and then watch them melt, and the level of the water won't change.
Interesting.
Try it tonight when you have a drink.
I'm going
sure
to do
you probably
that.
will
I'll
after
have a couple.
This. Exactly.
After this show, maybe 3.
You'll need them. And so, but it's the ice that's on the land that melts and goes into the water that raises the sea levels. But our Arctic is incredibly warm. In some places, some people have said the average last year was more than 30 degrees warmer than average. But interestingly, as those things change, for example, Northern Europe will get colder because the Gulf Stream will disappear. The Gulf Stream keeps Northern Europe warm. So when people say, oh, it's been a cold year here or there, they don't realize that global warming is not uniform. And as we've said in this program before, it's going to differentially affect people in different regions. And unfortunately, The people that are probably going to be hurt the most are people in the equatorial regions, who are the people, the poorest countries, the people who are least likely to be able to, New York can build walls in principle around, and Donald Trump can build walls everywhere for all, and in Florida around his Mar-a-Lago southern White House, which is going to be underwater.
It's going to be a capital M, Mar.
Yeah, and so, but the poor countries are not going to be able to do that.
So basically, we're talking about rising sea levels, loss of Arctic sea ice. What about things like heat waves, droughts, flooding situations, too much rain in too quick a time?
The interesting thing is that people have been hesitant to say, oh, this extreme heat is related to climate change, because local weather changes by the El Nino current, which makes things warmer for a while and then gets colder. So people have been hesitant. But but you can do things statistically, and the number of extreme heat events has increased to the point that you can definitively say that global warming has produced a number of extreme heat events. And in fact, there are areas of the globe right now that are close, but will, by the year 2050, be uninhabitable. People will not be able to live outside in those areas and survive, because above a certain temperature, the human body can't release heat enough. So you'll actually not be able to stay outside during the day in certain areas of the globe, but near the equatorial regions of the globe.
All right, critics, obviously, they're out there, and I want you to explain, because I'm researching this, and I'm hearing from the deniers, and we'll hear from the deniers after you're on.
Yeah, they will.
Here's some of the points. Research shows solar activity is causing climate change.
Well, solar activity takes place at all times. First of all, there's an 11-year solar cycle, which we know about, but that hasn't produced climate change. Solar activity changes over the course of 2 billion years and will make the Earth warmer. But you can show that the changes that have been taking place over the course of this past decade can in no way be explained by solar activity. In fact, as we said before, it's simple high school physics. You calculate the amount of heat coming in the Earth, the amount of heat that's stored, and you see it in the temperature changes in the ocean and the air, and you can work it out. It's just simple energetics. The solar activity cannot be responsible for it, and certainly solar cycles, which have been periodic, which happened over 11 years, have been periodic for a long time. But what we're seeing now, and maybe you'll have graphics to show it, is over time an extreme change over the last 20 years.
We don't have graphics to show it.
You don't have the red spots?
No, that's our graphic right there. What you just did is our graphic.
Okay, that's my graphic.
All right, human-influenced warming. Human-influenced warming is a hoax, they say.
Well, and you can say that pigs can fly, but it doesn't mean it's true. The point is, there's no evidence. The climate scientists are not making money off this. They're doing data analysis of what the carbon dioxide levels are, what that will do by simple physics and chemistry, and then looking at the output. As I've told you before, if you don't like global warming, you think it's nothing to do with carbon dioxide, even though the physics tells us it should. When you have a soda pop in a can, you open it up, tastes nice and tart. That's because the carbon dioxide is under high pressure. It dissolves in the water, forms carbonic acid, which makes that nice tart taste. You leave it out for a little while, the carbon dioxide goes away, it tastes stale. Well, the same thing happens on our oceans. As carbon dioxide levels increase, the carbonic acid in the oceans increases, the pH level changes. We've been able to measure that. That's producing bleaching of corals. We can see the pH level changing exactly as you would expect because the carbon dioxide level is changing. Science works.
You mentioned that scientists aren't getting rich off this. There is an argument that scientists are increasingly moving on to the idea of human-caused global warming for research grants. It's the only way you can get a grant these days.
You get grants by studying the climate and doing better models. And you don't get more money if you discover the world is heating up. Or, in fact, as I've told you, as we've also said in this program many times, if you're a scientist, the way to get famous is to show your colleagues are wrong. So in fact, if you could do a better model that showed that the other models were wrong, you'd become recognized for it if you could show the model work.
Okay, I didn't make all this stuff up. This is out there. These are people
people are making it up.
But how is it that these arguments have sustained for so long when so much of science seems to say, how do you address global warming?
Well, I think there's a lot of factors, and one, unfortunately, is money. That, in fact, there's a long history of the fact that, for example, the fossil fuel industry knew for a long time, ExxonMobil, that global warming is happening, but in fact for a long time denied it. Now they realize it's happening, they're trying to respond by going into new energy sources. Unfortunately, money talks, and more money, the media is responsible in some sense, more money is spent propagating false news about climate than the entire budget of the Intergovernmental Panel on Climate Change. And if you can spend more money in the media and get that information out, unfortunately, in the modern world, you can propagate false stories. And there was a false story that's affected things now.
Let's talk about this. It was first reported in the Daily Mail, given credence by the U.S. House Science Committee, the idea that we are in for the biggest cold snap here. We've seen dropping temperatures, and we're going to experience hugely dropped temperatures here, which means global warming is a hoax.
Yeah, the House Science Committee that's almost an oxymoron lately, because Lamar Smith, who's the head of the committee, is a huge climate change denier. Most of his money, by the way, has come from the fossil fuel industry. And they quoted an article by, guess what news source, what reliable news source? Breitbart News. And which said, climate drops by an unprecedented level, 1 degree, climate change is a hoax. And the point is, it's not true. First of all, they cherry-pick the data. There is El Nino, and El Nino, which we know about in Arizona very well. It affects the climate. And so there was a peak during El Nino, and the climate and the average temperatures dropped. But if you had the graphic that I hope you'd have, it shows that, of course, there are fluctuations over years, but the drop this year is by no means the largest in recent memory, which they say. Moreover, they just looked at the land temperatures and not the land plus ocean temperatures. If you look at the land plus ocean temperatures, then in fact, between October and November, it went up again. It didn't go down. So you can always, if you believe you know the answer in advance, you can always cherry pick the data to find out what you want, but that's not the way science works.
And yet the critics, the deniers, one last point here from the deniers' point of view.
Okay, if you want to be that way.
They say you're an alarmist and you're cherry picking data.
Well, the point is you can say it, but look at the data. Look at all the data and look at it for yourself. And in fact, you can see there was a Washington Post story that showed all the data and explained why the Breitbart result was wrong. And you got to ask yourself, as I always advise people, when people are making claims, you got to ask, do they have anything to gain by that claim? Now, you got to ask, are representatives of, say, the fossil fuel industry, is it in their interest to suggest global warming isn't happening? And then compare it to the climate scientists who are just doing modeling. Is it in their interest? And you've got to be skeptical. But the key point is, obviously, to be skeptical of what you read and look at the sources. And certain news sources have been known to be rather extreme. And unfortunately, the House Science Committee, for example, was when the New York Attorney General tried to, in fact, indict ExxonMobil for the known fact that it knew information was propagating false stories there. The House Science Committee tried to, in fact, ask the scientists involved to subpoena them to get all their information, because they didn't want that story to come out, and they felt that somehow that was muzzling ExxonMobil. So there's been, unfortunately, and it's of great concern now, because of, as you know, in the current administration, there's a great number. In fact, the person who is heading the transition for the EPA is someone who's denied the existence of climate change and simply lied over the years. So the public right now has to be more skeptical than ever, because if the government is skeptical, it's okay. But if the government has bought into these lies, the only place to change that is if the public is responsible enough to listen and be skeptical of what they hear.
All right, you want to do something other than weather here?
Yeah, I wanted to get to the good stuff. We start with the bad stuff.
Climate, because climate and weather are different things.
Good point.
Thank you.
Exactly. Weather is a daily basis. Climate changes over short term and long term. And the short term changes we're seeing, which can only be explained by human development. But it's different than, if it's cold here today in Phoenix, which it is, it doesn't mean that global warming isn't happening.
All right, let's get to some physics.
Let's get to some
physics.
Let's get to holiday. I don't want to say Christmas. I want to say the holidays. Except for you, I'm going to say, I've got a Christmas present for you.
What's my gift?
I know that you love quantum mechanics.
I love it.
I know that you love quantum weirdness. So the rest of the program, pretty well, will be about quantum weirdness. And in fact, I was thinking about this in the green room. I was talking to your producer about it. And here's why Christmas and quantum weirdness are so important.
Okay.
Do you know how Santa Claus gets to all those houses?
I don't.
Yeah, how can he go through all the houses if he takes 1 second per house?
I know.
How can he do it?
I know.
How what?
There's more than one Santa Claus.
That could be, but not necessarily. If Santa Claus was a quantum person,
Right.
then Santa Claus could be in many places at the same time.
Schrodinger's Santa Claus.
Yes, Schrodinger's Santa Claus. Quantum mechanics, as we've often said, allows particles to act in weird ways, and particles act like they're doing many things at the same time. So if Santa Claus somehow was quantumly coherent, his wave function could be in many different places at the same time. He could drop his presents off at the same time. As long as no one was there to measure it when he was dropping them off, he could be doing many things at the same time. And then the next morning, everyone could measure it.
That son of a gun, that's Santa Claus.
That's the only explanation I know of. Well, that, of course, is farcical, but what we've discovered and what is really interesting is that technology is exploiting the weirdness of quantum mechanics on a daily basis. And I thought I'd pick 4 stories that demonstrate that.
All right,
so
the first one is that photons can change color through quantum mechanics.
Better than that.
Better?
No, better than that.
All right.
So I told you that, let's say, an electron can be doing many things at the same time. For example, electrons are spinning.
Yes.
And we use this fact that electrons can be spinning up and spinning down, spinning in different directions at the same time, until we measure them. Then we measure they're spinning in one direction. But before that, they're spinning in both directions. Or you can't say which direction they're spinning at all. They're spinning in all possible directions at the same time before you do the measurement. Like it or not, that's the way the quantum world works. Well, what's also been discovered is if you put photons through a dense media, then they can actually interact and change their color. It's called nonlinear optics. Okay, so we can measure photons of one color changing to another color. That isn't so surprising, but what's been done here is to use the quantum mechanical aspect of that. When photons go into that dense medium, there's a probability that the photon will change its color. But if you haven't measured it, then the photon can be in a superposition of 2 different colors at the same time. And it's weird, but a photon can have 2 different colors at the same time. A particle of light can have 2 different colors, a quantum mechanical superposition of 2 different colors. If you measured it, you'd measure one color or the other.
Right.
But it's been actually being allowed to use. The fact that it's in a superposition of 2 different colors means we can store information. We can call this a qubit, a quantum information storing device, just like whether we use electrons spinning up or down to store information. So this group has actually used the fact that the photon could be in a superposition of 2 different colors at the same time to store quantum mechanical information.
But what if you want to go to the information on the one color and find out it's the other color? Is the information lost on the one color that's not there anymore?
Well, the point is, you can do all sorts of manipulations on the photon before you measure it. So you can use it to store information.
It's a holding device.
And do quantum mechanical calculations where it's doing 2 things at once, and then afterwards measure the outcome. So you're not measuring it during the process where it's doing its crazy stuff.
But it's hard to go back because once you're gone, right?
Well, once you've made the measurement, it's all bets are off. But during the time it's doing its stuff, it actually has 2 colors at the same time, and we can use that to store information and do miniature kind of quantum computing. So
Schrodinger's photon.
Schrodinger's photon. Okay. Until you measure it, it's alive and dead, red and blue at the same time, which is wonderful for people like me who are colorblind, because most things are red and blue at the same time.
All right. There's also a new gravity measuring device that uses an atom chip, an ultra cold atom.
What the heck is that?
Well, there it is. That's what the heck that is.
Oh, there it is. It's a little chip. There you can see it right there, an artist schematic. But the point is, for a long time, we've been using photons and electrons and using the properties of photons, the fact that they can be in many different states at the same time, to use quantum mechanics. But now we're able to take ultra-cold systems of atoms, which basically are so cold that all the atoms form a single quantum mechanical state. It's called a Bose-Einstein condensate. And then a whole group of atoms acts like a single quantum mechanical state. And then what happens is, that means if you send that group of atoms from one place to another, they act like a single quantum mechanical object. And that means they can do many things at once.
Again?
They can do 2 different paths at the same time. And then the final state of those atoms will depend upon what the atoms have experienced over the 2 different paths. If there's a gravitational field, then as the atoms go one way around it, they're basically what's called their phase. One property of the atoms will be different than the atoms that have gone the other way, and the atoms can actually interfere with themselves. And you can try and measure that by seeing the fact that you get an interference pattern of atoms that's different because there's a gravitational field than if there wasn't a gravitational field. It's like waves interfere. As you've seen, waves will form troughs, and a single electron can be in 2 places at once and interfere with itself. Now whole groups of atoms big enough groups of atoms, so-called Bose-Einstein condensates, can be sent, and they're big enough to be measured to see interference patterns produced by those atoms. That's what you're kind of seeing with those dots on the left-hand side. And the pattern of those dots will be different if there's a gravitational field than if there isn't. Bottom line is you can use the fact that atoms in a quantum mechanical state can be in many places at once to probe a gravitational field, because the gravitational field will do different things to the atoms as they go on different trajectories.
And because it's so small, because we saw that huge hand holding up this little thing, so you could put that like in a backpack or take it anywhere. You could put it on a bird.
To measure gravity has generally been a difficult thing because gravity is so weak and you nearly need heavy objects to do it. Because these things are so sensitive, because you're using quantum mechanics, you can measure gravitational fields in principle, and this is just a prototype, with small objects.
Would you want to put it on a bird?
You certainly might. It might. I mean, you never know. I mean, you could imagine that you could probe the trajectory of where the bird has gone.
See?
You never know.
See?
You know, you could be way ahead of your time, Ted.
Yes. Nano laser. We're running out of time here. Speaking of time, what is a nano laser, and why do we care?
Well, here's the thing. Particles act like they're waves, and waves act like they're particles.
There's a nano laser.
Big deal. It's a little. People have created lasers that are so small, they're microscopic in size. Now, light has a wavelength. The reason microscopes can only see objects of a certain size is because waves like light can only probe objects of the wavelength of light. If you have ocean waves, okay, and you put a little pebble in there, the ocean waves will go by without even noticing it. But if there's a big dock, then you look behind the dock, you'll see a spot where there's no waves.
Right.
The waves will get disturbed by objects that are the size of the waves and not much smaller.
Gotcha.
So that's why light microscopes can only see things that are the wavelength of light, which puts a limit on light microscopes. But what's really neat is these little lasers they actually generate light of a long wavelength, but the lasers themselves are smaller than that wavelength. And what you can do with probes is, if you embed these in objects, you put a probe over the object and excite the nanolaser, boom, you see a light wave coming out, and you see it coming from a region much smaller than the light wave. So you can use the laser to actually allow you to make microscopes that are much smaller than the light that you're using to probe the system.
We're talking maybe biological tissue, like cells and things?
You can actually, in principle, embed these little lasers in, and even though the light is a wavelength that's this big, that wouldn't see the little cell, because the laser's so small, when it gets excited, you can see that it came from that cell, and you can probe systems that are much smaller. It's tricking the system. It's somehow overcoming this limit of wavelength. That's pretty exciting.
That could be pretty useful stuff.
We are in an era, the 21st century, of using quantum mechanics, new technology, to allow us to do a whole bunch of things, because we're beginning to be able to exploit quantum mechanical weirdness. It's quantum mechanical magic, and this is a magical season.
It is. It's the most wonderful time of the year.
It's the most wonderful one, and this is the most wonderful time of physics.
All right, we're running out of time here, but I want to get up to quantum cryptography, the idea of securing information from city A to city B by way of quantum mechanics. Look, there's city A and city B, by the way.
Bob and Alice and Charlie and all these things.
Whatever.
The point is, because of this weird property of entanglement, as we've talked about before, you can entangle photons, individual particles of light, so they're quantum mechanically in a single state. And what that means is you can instantaneously transfer the state of one particle in one state to the state of another particle in another state.
Instantaneous.
It sounds like we've talked about quantum teleportation before. This allows you, in principle, to allow you to send coded messages. Because if you could have a message, let's say a large prime number, which is the key that's used to encode messages, and you can instantaneously transport it somewhere else, then someone else will have the quantum mechanical key, and they can use it to decode messages. And what's really neat is you can tell if someone's eavesdropping. Because if they're quantum mechanical, there are quantum mechanical correlations between the two states that can't be explained classically, and you can do measurements on the state that you're now looking at, which, if someone had detected it in the interim, would be different than if they didn't. So you can send quantum mechanical keys, which allow you to encode information, and better still, know if it's been eavesdropped. And what the new experiments have done with that picture is actually, the problem is we can't detect things perfectly, and these new detectors have allowed you to even overcome that effect and actually look for someone interfering, not just by looking for the original entangled photons, but by sending other photons back and forth to see if someone has been interfering.
Yeah, the interference.
So it may be a good way. In fact, what this has done is allow you to send messages that are encoded quantum mechanically 400 kilometers. So it really means not just over the size of a laboratory, but 400 kilometers, which is the kind of scale you're going to need if you want banks to be able to send information from one another safely. And that may mean that we'll be able to overcome lots of eavesdropping that might unsecure your credit cards, and I know how valuable they are to you.
We started with we started with a tough story. Now we're ending with a positive story because we got to go. We got to go.
We got to go, and the point is, this will make ultimately your Christmas credit card purchases safer.
Thank you. That's it for now. I'm Ted Simons. Thank you for joining us. You have a great evening.
Arizona Horizon is made possible by contributions from the Friends of Arizona PBS, members of your PBS station. Thank you.